So we will start in 2 minutes. Yeah. Am I audible? Yeah. So let's start. So hello everyone. My name is Srijal Mukherjee, and we will be solving some. This is the live session for NPTEL course on computer organization architecture. We'll be solving some sample problems which are related to week 8, like always. And the session is being recorded. So and if you have any doubt, you can ask the questions on the chat. I will respond to them accordingly. So let's start. So assignment 8 doubt I will not clear because those are your assignments. So you can ask those questions on your forum after the week are done, because those questions you have to solve. Those are not like it has been instructed to me not to discuss the assignment questions on this. But the problems which I will be solving are quite similar to the assignment questions. So I guess it will help you to solve the assignments, the problems I will be solving here. Okay, so this is the first question. For any binary number, shifting the fraction point by 2 position is equivalent to. So it is said that we have a binary number. So this is the fraction point. So if we suppose these are the numbers or something like that, like you can suppose. So uh, if we shift the the fraction point by 2 position, so what will happen by to the left by 2 positions, like we are shifting it to the left. So to the left. So what will happen? So if I have gone through, this is the question similar to the question that has been asked, you say mostly in the basic C questions you have like encountered previously. So suppose if you have uh, gone through a C lecture, so there is this symbol called it's like left shift. So if we do this, what does this mean? This means we are dividing the number by 2. Again, if we shift the number by 2, this means we are dividing the number by 4. This is one bit. Similarly, if this happens, this is x divided by 8. Now the consider the corresponding one. So what happens if we do this? This means we are actually multiplying x by 2. Similarly, if we do this, it means you are multiplying it by 4. So the correct answer is here in this case, if we shift it by the left by 2 positions, then we are basically dividing it by 4. So the correct answer is A. Okay, so this was the first question. So this was a very easy questions. Like we will come to more difficult questions correspondingly after this. So let's get to this one. So the interpretation of a single precision floating point number. This is the number. So in IEEE 784 format will be. So what does this number represent? So if you look in this number, let me divide it into few parts. This is 1. This is the first bit. This is the next 8 bit, and the rest 23 bit. So now if you have gone through the lectures of this week, you will remember that in IEEE 784 there are few things. The numbers are basically divided into 3 parts. So one is the sign bit, then you have the exponent, and the last is mantissa. Right. So now there is also this table, if you remember from the lectures. Suppose value of E is 0, that is the exponent part is 0. So if you remember correctly, this is the exponent part, and this is the mantissa part, right? So if exponent is 0 and mantissa is 0, what happens? So value is basically exact 0. Next, if the exponent is 255 and the mantissa is 0, exponent 255 means this one is all 1, this middle part is all 1, that is 8 bit, so that is 255. So that represents that the value is basically infinite. Next, if E value is 0 and M value is not equal to 0, then what happens? We call this a special kind of numbers called denormalized numbers. Right, so these are the special kind of numbers, denormalized number. What does this represent? This represent numbers which are not zero, but they are very close to zero. Right, and the last kind of is the exponent value is 255 and m value is not equals to 0. That is we call not a number, none. Now what is the case that is given here? In this case you will see the exponent part is 0, but the mantissa part is, there is a certain number that represents the mantissa part. So which of the following options it represents? It represents this one, denormalized. What does it? It is numbers that are very close to 0. So the correct answer is option B. It satisfies these conditions. So if you have any doubt, you can ask regarding this. So I will move to the next question then, if you don't have any doubt regarding this. So this is the third question. The question says, consider the following statements. IEEE 784 floating point representation requires shifting of mantissa for multiplication and division operations. And that statement 2 is shifting of mantissa affects exponent value of that number. Which of the following statement is correct? You can write the answer in the chat. I will then start. Let me see how many of you can do it this. So let's look at the statement 1. So statement 1 says that IEEE 784 floating point representation requires shifting of mantissa for multiplication and division operations. So this is false. The shifting operation is only required for addition and subtraction. is necessary only for addition and subtraction. Now now the statement 2. Statement 2 says shifting of matrices affects the exponent value of the number. This one is true. So let me give you an example. So if we shift the mantissa by three positions to the left, so what happens? So if we like if we shift m to left by three positions, so what happens if we shift left m by left to the left by three positions, right? So what happens? So we need to, so in that case, to maintain the like it affects the exponent value. So in order to maintain it, we need to uh, decrease decrease e by 3. So if we shift m to the left by 3, so if we shift the mantissa by 3, then we have to we are if shifting left, we have already seen in the first example that shifting left means we are basically dividing it by 8, right? We saw that shifting the fraction basically means division or addition. So shifting left by the three positions means we are dividing the number by 8. So like as a result, we need to decrease the exponent by 3 to maintain the correct value. So the correct answer in this case is option B. Right. So let's go to the next one. So now these are the these are problems which are mostly a little bit advanced, but like if you like able to solve it, then you will be able to solve most of the problems relating to these floating point questions. So so it is given that the following binary number in 32-bit single precision IEEE 784 format. So what is the corresponding decimal point value? That is the question, right? So let's so these are 30. This is 32-bit number. So there are 32-bit entries. So let's divide this into three parts, right? 1, right? So we have divided it into three parts. So as we know from this, from the number we can see that s equals to 0. Now we all know how the fraction is represented. A fraction of IEEE 784, it is represented as minus 1 to the power of s into 1 dot m into 2 to the power of e minus 127. So from this number, what is the value of s? Like we have divided it into three parts. First bit is the s. S value is 0. The next 8 bit represents what? The m part, the mantissa. No, sorry, the next m bit represents the exponent. So this is the exponent part. So this is the s, this is the e, and this is the m part, and this is the s. So e value, that is the exponent value, in this case is 0, 1, 1, 1, 1, 0, 0, and the m value is 1, 1, 0, 1, 1, 0, 1, right? So this is the value that we get from the IEEE 784 for a representation of the floating point number, and the corresponding fraction is this, right? So few thing is, what is the value of e now? So if we like calculate the value of e, it will be 0, 1, 2, 3, 4, 5, 6. The corresponding decimal value is 2 to the power of 6 plus 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 2. So if we calculate, it becomes 64 plus 32 plus 16 plus 8 plus 4. So that gives the value of 124. So E value is 124. Now we have to find the value of, so A is given is 0, so this is becomes minus 1 to the power of 0 cross multiplied by 1.0, like what is the value of m here? This, so this becomes 1.1101 into 2 to the power of, we have already found out the value of E, that is 124 minus 127, so it becomes 1.1101 into 2 to the power of minus 3. So we need to calculate what is the decimal value of this. Simple, what we will do, so this becomes 1, this one stands as what it is, then this is basically 0.5, then this next one is 0.25. Now this one is 0, so the portion of 0.125 is gone. So the next, that is again divided by 2, it becomes 0.0625 plus this one. So again we will divide it by 2, it becomes 0.03125. Next, this one is 0, that is this one is 1. So for this one you need to divide this by 4, so it becomes 0.0078125 into 2 to the power of minus 3. So if we add this up, this whole, it comes down to 1.8515625 into 2 to the power of minus 3, and the correct answer will be then 0.2314, and there will be some other decimal digit numbers. So this is the final answer. So this is the step that you will need to follow to convert any like floating point IEEE 784 number. So if any question is given that given this is the IEEE 754 number, so what will be the corresponding decimal value? This is the whole problem, like the set of like flow that you need to perform to get this answer. So if you have any doubt regarding this, you can ask. This is a very like important problem. Should I repeat it once more? Yeah, fine. I will do it again. So if you see, this is the IEEE number that we have been given. So we'll so you know, so in IEEE 784 you have 1 bit of S, that is the sign, 8 bits of exponent, the next 8 bits are exponent, I have mentioned here, that is the next 8 bit, and the last 23 bit is mantissa. So the corresponding number in decimal can be written as this: f equals to -1 to the power of s into 1.m, m is the mantissa part, and into 2 that is e minus 127, e is the exponent part. Okay, so what we have found out here is the s value is 0 from this number, e value is this like 0 1 1 1 1 1 0 0, and the last part is mantissa. So this is the mantissa. Ignore the, like, you will ignore the other zeros, only you will check the leading zeros up to the last one. So this is the mantissa part, like up to here you need to like take it out from this 32-bit number. So we found out what is the binary value of this exponent. So if you see, this is like this is the conversion which we have studied in the earlier classes. So it is 2 to the power 6 plus 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 2. So that is 64 plus 32 plus 16 plus 8 plus 4. If we add this up, it will come down to 124. Correct. So in this step, we substitute the values of m and e. So m value is this, e value is this, that is 124 we have substituted here, and that is minus 127. Now the next step is you need to convert this binary number into decimal. So how we will do that? So yeah, if you have gone through the lecture and previously also we have studied how to convert a decimal number to like binary number to decimal. So this will be 1 1. So if this one is the case, so what we'll do, like like if it is 0.11001, what we'll do, that is 1 into 2 to the power of minus 1 plus 1 into 2 to the power of minus 2 plus 0 into 2 to the power of minus 3 plus 1 into 2 to the power of minus 4. So what is this value? This is 0.5. That is only I have done. So this is 0.5. This one represents 1 into 2 to the power of minus 2. That is 1 divided by 4. That is 0.25. Then and the rest basically this value, and we have to divide it by 2, then this value will come. The next 0 is gone, so we need to consider it. So this one, how to calculate this one? You simply divide it by 4, this one will come. Next one, for this one you just divide it by 2. Next 0, when you don't have to consider this. Then for this one, what you will do, you will divide it this by 4, right? And the 2 to the power minus 3 trailing is remaining. So if you add this up, this value will come, and if you then multiply it, divide it like multiply it by 2 to the power minus 3, then the value 0.2314 will arrive. So this is the final answer. Clear? This is a very important sum. Like we will solve more questions regarding this in the coming problems. So let's go to the next one. So it is given now. This is the inverse one. The previous one was converting a decimal number, like a floating point binary number in floating point IEEE 754 to a corresponding binary. Now we are doing the exact opposite. We are converting a decimal number to the corresponding binary. So let's start how we are doing it. So it is given the decimal number here is 0.5. So the f is f is 0.5. So how we will write this? So we can also write it like this. So you can write it like this: minus 1 to the power of 0 into 1.00 into 2 to the power of minus 1. We can write like this, simple, because this represents 1 divided by 2, that is 2 to the power of minus 1. Simple. Now like this value is basically 1, minus 1 to the power 0 is 1, and also 1. So this like if you consider that to the formula that we have discussed, that is 1 minus s into 1 dot m into 2 to the power of e minus 127. What is the, like, now you can see the similarity, right? Like if you match the equations, so what is the value of s? S of value is 0. What is the value of m? M is 0 0, like m value is 0. So if we write in the equation, it will be all series of zeros, that is this all will be 23 bit of zeros. And what will be the value of e? E will be minus 1 plus 1 127 equals to 126, right? So the correct answer, so this is the way we are doing the converse, like this is the converting the decimal to the corresponding binary, like the binary. So the correct answer is option B. Like the fraction bits is 0 and the exponent value, as you have seen here, is -1. Yeah, I will repeat again. So if you have plus 127. Yeah, this comes from this, like e minus 127. So that is what I am saying. Like if you represent it in the exponent bit, like we have seen in that, like 8-bit exponent. So 8-bit exponent, there this value will be, so this s will be what it will be. S will be 0. The 8-bit exponent will be 126 and the rest will be 0. So I will repeat once again. So given we have a decimal number 0.5, we have to find out the corresponding IEEE single precision floating point representation. First, what we need to do, so we can write 0.5 as this. 0.5 is basically 1 divided by 2, that is basically 2 to the power minus 1. That we can also write as minus 1 to the power of 0 into 1.00 into 2 to the power minus 1. Correct? Now, what is the actual like equation? This is the actual equation which we solve again last problem. Minus 1 to the power of s into 1 dot m into 2 to the power of e minus 27. So if you compare these two equations, what you will find? S value is 0, s value is 0, m value is 0. So this will be 23.0, and what will be the e value? E value is here minus 1. So we can write this like this: minus 1 is equals to e minus 27, or e value is minus 1 plus 127, that is 126. So the correct answer is option B, that is fraction bits is 0, 0, 0, 0 and exponent value is minus 1. We have seen already exponent value is minus 1. Now it is clear? Yeah. So I have done two problems. One is converting the decimal to floating point and floating point to decimal. So the next problem will be combination of both. So read the problem carefully, you will understand what it says. So consider there are three registers R1, R2, R3 that store numbers in IEEE 784 single precision floating point format. So we have been given three registers R1, R2 and R3, and all of them stored numbers in floating 784 IEEE 784 single precision floating point format. So assume the R1 and R2 contain the values these 0x422 5 zeros and 0xc12 and all the rest zeros. So these are hexadecimal numbers. These are basically IEEE floating point numbers represented in hex. So if we store in R3 R1 divided by R2, so what is the value that is stored in R3? That is we need to find. So let's get to this problem, and this is basically an easy calculation, but you need to, it is a laborious job, nothing more. So let's start it one by one. What is in R1? R1 stores 0x 4 2 2 0 0 0 0, right? So this is in hex format. So in previous classes I have shown how to divide, how to convert a hexadecimal number to the corresponding binary number. We know, so we'll convert each of the particular digits into their corresponding binary, right? That is the common notion. So what you will get? You will get from here, I will like it will require a little bit of space, so I will start from here. 0 1 0 0, 2 is 0 0 1 0, 2 is 0 0 1 0. Now there will be 5s, 0 0 0 0, 0 0 0 0, 0 0 0 0, 0 0 0 0 0. Sorry, R1 is given as 0x 4 2 2 0 0 0 0. We need to convert the convert it into into binary. So what is 4? 4 is 0 1 0 0. What is 2? 0 0 1 0. What is 2? 0 0 1 0. The next all fives are like all five are zeros, so it will be 0 0 0 0, 0 0 0 0, 0 0 0 0 0, 0 0 0 0, 0 0 0. Right, so this is the corresponding IEEE 784 number in binary. Now next is we need to divide it into the S, M and E, like we have already done in the previous questions. What it will be? So this is the S, first bit is S, next 8 bits. What it is? It is the exponent. S exponent, and this is the mantissa, right? So S value is 0, E value is 1 0 0 0 1 0 0, right? And what is the M value? 0 1. So what is the E value? So if we calculate, what it will be? 0 1 2 3 4 5 6 7. That is 2 to the power of 7 plus 2 to the power of 2. That is 128 plus 4. 128 4 is 132. Right? And so what is the fraction we are considering here? The fraction value is minus 1 to the power of 0 into 1.01. This M part comes here, into this is the M part, and this is the now the E part, that is 2 is 132 minus 127. So it comes down to, so what is this? Is basically 1 plus this part is 0, that is 0 into 2 to the power of minus 1 plus this part is 1, 0 into, no, not 0, 1 into 2 to the power of minus 4 into 2 to the power of 5. So it comes down to, so if we calculate this, it will be 1.25 into 2 to the power of 5. So this is the value of R1, right? We have got the value of R1. Our final target is what is the value of R3. Now we need to calculate what is the value of R2. Okay, so let's calculate the value of R2. R2 is given as 0xC120000. Fine, this is the value that is given, like what we did previously. So what we did previously, we converted this into binary and then proceeded the next. We will again do the same thing here, right? What we do, like we need to convert this into decimal. So what we do, what is the value of C? C is basically 1100. Next is 1, 0001. Next is 2, 0010. Next there are 5 zeros, 0000, 0, 0000, 0, 0. Correct. So this is the corresponding decimal. Now, like previously, we will again do the same thing. We will divide it into S, M, and E. So this is the S part. This is the M part, the E part, and the rest is the S part, like M part. So this is M, this is E, and this is S. So the fraction, so the S is basically 1, E is equals to 1000000, 10, and M is 01. So what is the corresponding fraction? So if we calculate E, what will be the E value? 0, 1, 2, 3, 4, 5, 6, 7. That is 122 to the power of 7 plus 2. That is 128 plus 2. That is 130. So the fraction is minus 1. S value is 1 into 1.01, this value M, then 2 to the power of 130 minus 127, right? So comes down to minus 1 into what is this 1.01, so it will be 1 plus this is 2, so that is 1 into 2 to the power of minus 2 into 2 to the power of 3, that is minus 0. So that is minus 1.25 into 2 to the power of 3. Clear? Just like previously, we do again the same thing. We convert it into the hexadecimal to decimal. Then we like strike out what is the S, E, and M. E value is 130, M is 0.1. So this all comes down to 1 minus 1.25 into 2 to the power of 3. So we have now got the value of R1 and we have also got the value of R2. So next let's find the value of R3. So what is value of R2 and R3? R2 we have find out. Sorry, R1 by R2. Right, so we have got it as 1.25 into 2 to the power of 5. That is the value of R1. So that is 1.25 into 2 to the power of 5 divided by R2. R2 is minus 1.25 into 2 to the power of 3. So that is minus 1.25 into 2 to the power of 3. That is minus 2 to the power of 2. Right? This is the final one. So now we can write R3 as minus 1 2 to the power of 1 into 1.0 into 2 to the power of 129 minus 127. Correct this one? So like from the previous one, like when we solve the question number 5, we show how to do like the decimal, like converting the decimal 0.25 to this. So this is how you need to like reverse engineer it. So what is the value of corresponding M we are getting? S value is 1. E is equals to 129 and mantissa is 0 0 23 bits. So this 129 can be written as 1 0 0 0 0 0 0 1. Correct? This is how we can write 129. So the corresponding like the IEEE 784 floating point number is 1, the S value, then the E value will come 1 0 0 0 0 0 0 1, and the rest will be zeros, or 23 bit of zeros. 1 2 3, this will be all zeros. So this is the first hexadecimal number, this is the second, this is the third, and rest all are zeros. So R3 is basically this one is, what is this one, 8 plus 4 12. 12 is C, C 0 8 and rest are zeros, 5 zeros. So this is the answer. The correct answer is option B. What is the value of R2? R2 we calculated, right? Here we have calculated this value, right? Minus 1.25 into 2 to the power of 3. This is a lengthy process, but it will help you solve both problems at one time. The conversion of number from floating point number to corresponding decimal number, and the reverse one also, that is the converting the decimal number to corresponding floating point number. So you like, so that is the like last one regarding this floating point numbers. Like this is self-explanatory. If you like, if you have like how we solve question number 4 and 5, similar we are just solve the question number 6. Sir wants R3 calculation. Yeah, R3 calculation I'm showing again. So what we are doing is here R1 is divided by R2. So like the calculation of R1 and R2's number to decimal is correct, right? You have understood that. So that is basically 1.25 into 2 to the power of 5 divided by 1.25 into 2 to the power of 3. That is basically minus 2 to the power of 2. So like I showed in that problem of converting 0.5 to corresponding like decimal. So like similarly that is a similar way. So basically we can write this as minus 1 to the power of 1, that is for this minus, into 1.0 into 2 to the power 129 minus 127, that is 2, right? So E value is 129, M value is all zeros, and S value is 1. So now E value is 129. 129 is basically 1 0 0 0 0 0 0 1. Right? We'll write the corresponding this as this. So 1, then the E part, here 8 bits of E, and then the rest are all zeros. Now we need to convert it back into hexadecimal. Now how to convert back into hexadecimal we know. Each byte take 4 bits and convert it into hex. So this one is C, this one is 0, this one is 8, and the rest all are zeros. So let's go to the next problem. So this is the next part of the lectures that were there, that is regarding the pipelining. So the question is, we have a 6-stage pipeline with stage delays 45, 20, 15, 42, 23 and 20 nanoseconds respectively. So ignoring the delay of latches between the stages, the total time required to process, what will be the total time required to process 150 sets of data? Simple problem. This is like similar to the equation that has been given. So E is equals to, so we have if we have a K stage pipeline, what it is? So time taken will be K minus 1 plus the n, that is the number of data sets, into tau. Tau is the clock period. So what is the tau in this case? Tau is minimum clock period, the delay of the slowest stage. Delay of the slowest stage. So we have been given a sets of delay here. So if you notice 45, 20, 15, 42, 23, 40. So what is the slowest stage? That is the slowest delay, that is 40. So 45. So 45 nanoseconds is the clock period. So, and what is the value of K? K is 6 stage pipeline. And what is the value of N? You are processing 150 data sets, 1500 data sets. So if we substitute this value here, you will get the answer. T equals to 6 minus 1 plus 1500 into 45 ns. So if we calculate this, this will come down to 67725 nanoseconds. That is 67.725 microseconds. So this one is clear. This is pure formula. There is nothing else to do here. We will substitute the value of K, tau. Tau is the delay of the slowest stage. So if you see, the largest number here is for between 45, 20, 15, 42, 27, 20. That is 45. That is the slowest stage. So that is the value of the clock period. Then we have the N, like N equals to 1500. That is the number of data sets where here. And then you will substitute the value and you will get the time required. Okay, so let's go to the last question. So this is a very important question. The question is, so you have given this reservation table, you need to find the MAL, the minimum average latency. This is another important question that are asked for this for these pipeline concepts. So let's start it. So first you need to find out what are the forbidden latencies. You have encountered the terms in the lectures. So what are the forbidden latencies here? To find out the forbidden latencies, you need to subtract the distance between every x in each row. So that is, in this case, you will see that is 1x is in for S1, that 1x is in 1, another is 5, another is in 8. So what is the difference between 1 and 5? 1 and 5, the difference is 5 minus 1 is 4. So that is one of the forbidden latencies. Next, between 5 and 8, 5 minus 8 is 3. So that is 3 is another forbidden latency. And another is 1 minus 8. That is 7. 8 minus 1, 7. That is the third forbidden latency. Next, for S2, 2 minus 6 is 4 minus 6 minus 2 is 4. That is already we have added forbidden latency. Next forbidden latency is 8 minus 6, 2. So 2 have not added, 2 will add it here. Next, the other one is 8 minus 2, 6. 6 will not have added, we will add here. Next one is For S3 it is between, there are only two x's here, that is 6 and 3. So 6 minus 3 is 3, that is already present. So what are the forbidden latencies? uh, 2, 3, 4, 6, 7. Right, these are the forbidden latencies. So what is the max forbidden latency is 7. So we need to find out the collision vector. So what is the collision vectors? Collision vector we can write as C7, C6, C5, C4, C3, C2, C1. So you can see already the forbidden latencies are given as 2, 3, 4, 5, 6, 7. So these all we will substitute as the value 1. These are the latencies we can't use. 6, 7, 4, 3, 2. The rest that is 5 and 1 will be 0, because those are latencies are allowed. So here the so another thing is permissible latency. That is 1, 5 and 8 plus all latencies are permitted. So we have found out what are the forbidden latencies, what are the collision vector, and what is the permissible latencies. Clear? Let's now go to the next part. What we need to create the where we need to create the state diagram. So let's start building the state diagram. So what will be the first state? First state will be the collision vector state. That is, this one will be the first state. The collision vector state is 1, 1, 0, 1, 1, 1, 0. Okay. Now what are the what are the permissible latencies? 0, 1 and 5. So we need to find out the what will happen for when we use the cycle 1, that is the latency 1. So how we will do the next state? How we will find the next state? So this will be the collision vector 0, 0, 1, 1, 1, 0, and you will left shift it by 1 and or the value. So it will be 1, 1, 1, 0, 1, 1, 0. So for next state, so like for this one, for this like 1 latency, we shifted it by 1 and XORed it with the collision vector. We will always XOR it with the collision vector no matter what it happens. So or it, not XOR, or. So it will be 1, 1, 1, 1, 1, 1, 1. So this state will be 1, 1, 1, 1, 1. Right, this is the one state. Now for this state, if we the other, so here you see all of them are non-permissible latencies. So the only latency that is available to us is 8. So if we do CV of 1, 1, 0, 1, 1, 1, 0, and for latency 8, that means all all of them has been shifted to the left, so it will be all zeros. If we do it and OR, it will be 0 1 1 0 1 1. So the operation we are doing is OR. Okay, so it will return to the original state, right? So now the only one latency that is left, the one latency that is left we need to is 5. So what happens if we for 8 it will also be this state. If we consider this, for 8 if we do a if we use latency 8, it will come back to this state. Now the only remaining thing is what happens when we use 5, the latency cycle 5, right? What will happen? We will like instead of one shift, we will shift it by 5. That will be 1 1 0 1 1 1 0, and by shifting it by 5 we'll have only these two, 1 1 0 0 0 0 0. If we OR it, it will be 1 1 1 1 0 1 1. So this will be the state, 1 1 0 1 1 1 1. So now like previously, like what we did in this state, now there are two permissible latencies here. That will be 5 fifth digit and 8. Now if we do it 8 we will return again to this one, and if we do 5 it will be 1 0 1 1 1 0 and 1 0 0 0 0 0. So it will be 1 1 1 1 0 1 1. So it will return to the same state. So these are all the, this is the state diagram, right? So now from the state diagram we need to find out which are the possible cycles, possible latency cycles. So possible latency cycle. First one is 8, only 8. That is one possible cycle. Next we have is 1 and 8, that is one possible cycle. Another cycle is 5 and 8, that is one possible cycle. Another cycle is only 5 here. So these are all the possible cycle in the transition diagram. Now you need to check which of these are greedy cycles. So what we mean by greedy cycles? Greedy cycles is the cycles which starts at the the state at which starts, it always takes the minimum latency cycle. So if you consider this, there are only two greedy cycles. One is 1 and 8, because 1 here is the minimum latency at this state and 8 is the minimum latency in this stage. So this is one greedy cycle. Another is only 5, because 5 is the only smallest latency that is possible here. So it will be these two. greedy, greedy. Smallest possible arcs. So now I need to find the mal. So what is the minimum at like what is the average latency for this cycle? 1 and 8 is 4.5, and for 5 the average latency is 5. So the minimum average latency is this, right? So the correct answer is option B. So if you have any doubt, you can ask regarding this. I know it is a lengthy calculation. So if you have any doubt, you can ask, or shall I repeat it once more? From cycle 8, you can can you explain? Yes. Yeah, so if you look for cycle 8, basically for cycle 8 you will just like if you look at this, so all has been left shifted, all like for cycle 8 all 7 has been left shifted. So you will be just odding it with all zeros. So that means naturally for all cycle it will always point to this start like collision vector, the starting state, right? So if you do this also or this also, every time it will come to D, because sorting with odd will always come to the first state. And also it is necessary you remember always OR with collision vector, not any other vector. If you remain in any state, either this state or this state or this state, at every state you will just OR the shifted value with the collision vector. You will shift this or this, but you will always OR it with the collision vector. So if you OR it, it will always come to this part only. So if you notice from here, you will have like 4 cycles. This 1 and 8, only 8, 5 and 8, and only 5. So possible cycle, these are the possible latency cycle: 8, 1, 8, 5, 8, and 5. So out of this, if you check, 1, 8, and 5 are the greedy cycles. Why I'm calling it the greedy cycles? Because if you check in these cycles, in this state, what is the minimum latency? That is 5. So if 5 is present in this cycle, so that is why it is a greedy cycle. Again, if you look at this 1 and 8, in this state 1 is the minimum, and in this case 8 is the minimum. So in this cycle 1 and 8 both are the minimum arcs at their respective states. So that is 1 and 8 are greedy cycle. But if you notice at this cycle 5 and 8, is 5 the minimum latency at this stage? No, 1 is the minimum. So in this cycle 5 and 8 both are not the minimum latency at the corresponding states. So that's why this cycle is not a like greedy cycle. And same stands for 8, because 8 is not the minimum latency, 1 is the maximum latency. So there are 2 cycles that are greedy, that is 1, 8 and 5. And if we find out the average latency is basically here. One plus 8 divided by 2, that is 9 divided by 2, that is 4.5, and other latencies comes out to be 5. So the minimum average latency, that is mal, we say, is 4.5. So that was option 5, option B. Okay, so that was the last problem. Thank you for the like listening to the session. We will again meet next week, same time.